Okay, in this last video we're going to look at roller coasters and how we use roller coasters to figure out conservation of energy, apparent weight, and circular motion. And with those three concepts we can fully understand the ride that's going on in a roller coaster. Conservation of energy we can use to figure out the velocity at any point on the ride. Circular motion can be used to find the acceleration of the passengers at any point on the ride. And apparent weight can be used to find the force experienced by the riders. So let's look at an example here using a real roller coaster. The Millennium Force roller coaster at Cedar Point in Sandusky, Ohio was voted the top steel roller coaster in the world by 2011 by Amusement Today. I'm going to give you the data that I have for this roller coaster, and then we'll go and do a number of calculations for it. The roller coaster begins by lifting passengers up a 45-degree lift hill at 15 miles per hour to a height of 310 feet. After reaching the top, the train drops 300 feet down at an 80-degree angle. It then climbs 169 feet through a right overbank turn at 122 degrees from the horizontal axis, experiencing 4.5 Gs of acceleration. It then travels over a 182-foot, 55-meter parabolic hill, which provides the moment of airtime, 0 Gs. We will refer back to this page for all of our data. Now let's go through all the types of problems we can figure out using this data. I would like you to try each of these problems. So on your sheet, set up your sheet the same way you've done on other cases with two columns, one for your work, one for corrections, and do a problem. Then if you have corrections, put the corrections over here. Then draw a line, do the next problem on your own. If you have corrections, do them over here after watching mine. And keep doing that to receive credit for the notes for this video. Okay, in the first problem, how much work is required to lift a 45-kilogram girl to the top of the first hill? So we need the data for the first hill. The first hill is at a 45-degree angle, a height of 94 meters, and it's going to go at 6.67 meters per second. In this problem, we have a 45-degree lift hill, so we're going at 6.67 meters per second, a height of 94 meters. So in this case, our velocity is 6.67 meters per second. We have a height that was given earlier, 94 meters. We have an angle of this hill of 45 degrees. We want to find the work. So, in this case, we are looking for work. We can do work equals force times displacement, or we can do work equals change in energy. Now, in this case, we have the velocity of the roller coaster. We have the 94-meter hill, and we have the 45 degrees. So we know that at the top of the hill and the bottom of the hill, it's going to be traveling at a constant speed of 6.67. So what's really changing here is the potential energy. Now remember from earlier, if we have a 45-degree hill like that, what ends up mattering is the height, not the length of the hill. So that 45 degrees ends up not changing the way we would do the problem. So work is change in potential energy, in this case, since the kinetic is staying constant. So mgh final minus mgh initial. So the work here, 45 kilogram student, 9.81, final height of 94. Starts with the 45 kilogram student, 9.81, and an original height of 0. So we do 45 times 9.81 times 94, and we get a work here, 41,496.3 joules. Okay, how fast is the roller coaster traveling at the bottom of the first drop? So now we go back to our first data. It's going to drop 91 meters. So we know it's going to be 3 meters off the ground. It starts traveling at a velocity of 6.67. So in this case, our initial velocity is 6.67. Our initial height is 94 meters. Our final height is 3 meters, and we're looking for our final velocity. So we're going to use conservation of energy, 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. So 1/2, we don't know the mass of the roller coaster, we'll leave that as m. The initial 6.67 squared plus mgh, so m 9.81 times 94 equals 1/2 m v final squared plus m 9.81 times 3. So multiply these things out. 6.67 squared times 0.5, we get 22.2 m. 9.81 times 94, we get 922.14 m. Half mv final squared, and 3 times 9.81, so 29.43 m. So 22.2 plus 922.14 minus 29.43 gives us 914 m equals half mv final squared. M's cancel, so we divide by a half. We get 1829.82 equals v final squared. Take the square root. And this roller coaster would be traveling at 42.78 meters per second. Sorry about that. Now the next problem, at the bottom of the hill, has a 522 meter radius. What is the apparent weight of the girl? So we have a 42.78 meter per second velocity. We have a radius, 522 meters. So first thing we need to figure out is what is the centripetal force on this girl? So mass times v squared over r. So the centripetal force would be 45 times 42.78 squared divided by 522. We get a centripetal force of 157.76 newtons. Now, if we draw a free body diagram at the bottom of the hill, the girl will have the force of gravity going down and the force normal going up. Our centripetal force will be pointed towards the center of the circle. Since this is the bottom of a hill, our centripetal force will be pointed up. So our net force has to be 157.76. F net equals MA. But we already know F net, so we will do Fn plus Fg equals 157.76 newtons. I'm going to make up positive. So in this case, my force of gravity is going to be 45 times 9.81, which is 441.45 newtons. So force normal plus negative 441.45 equals 157.76. Add 157.7 or add 441.45 to both sides, and we get a normal force or apparent weight 599.21 newtons. So she would feel like she weighs an extra 157 newtons. Now we want the velocity at the top of the first overbanked hill. So let's go back to that data. The top of the first overbanked hill is 52 meters above the ground. So this will be a conservation of energy problem again. 1/2 mv initial squared plus mg hi equals 1/2 mv final squared plus mgh final. Now, I like to use my original data when doing these. So my original 6.67. That way, if I made a mistake at some point in the problem, I'm not carrying that mistake through the problem. So I start at 94 meters. I'm looking for my velocity. And my original height, or my height now, is 52 meters. So m times 9.81 times 52. So 6.67 squared times 0.5. Once again, 22.24 m plus 94 times 9.81, 922.14 m equals 1/2 mv final squared plus m times 52 times 9.81, which is 510.12. So 22.24 plus 922.14 minus 510.12 comes out to 434.26 m equals 1/2 mv final squared. Divide by 1/2. The m's cancel. So I get 868.52 equals v final squared. Take the square root. V final is 29.5 meters per second. So significantly slower than it was at the bottom of the hill, but definitely a lot faster than we started the ride. Now, what is the radius of this hill if the rider experiences 4.5 Gs? So we know the rider has a velocity, which we found in the previous problem, of 29.5 meters per second. We know the centripetal acceleration will be 4.5 Gs. So AC equals V squared over R. 4.5 Gs is 4.5 times 9.81, or an acceleration of 44.145 meters per second squared. So 44.145 equals 29.5 meters per second squared over R. Cross multiply, 44.145 R equals 29.5 squared. Divide, 29.5 squared divided by 44.145. And we get a radius 19.7 meters. And then the last question we want to look at is, what is the radius of the parabolic hill where the rider experiences 0 Gs? So in this case, as we look at, the centripetal acceleration will be 0. Let's go back and get as much data as we can. The top of the parabolic hill is 55 meters off the ground. So the height is 55 meters. I'm going to use my same initial velocity, 6.67 meters per second. My same initial height, 94 meters. Free body diagram here. We're at the top of the hill. We have force of gravity down. We have force normal up. And the centripetal acceleration in this case will be down. Okay, so let's look at what we have going on here. Now, in this problem, what we first need to figure out is the velocity at the top of the hill. So 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. So 1/2 m 6.67 squared plus m times 9.81 times 94 equals 1/2 mv final squared plus m times 9.81 times 55. Now if we look back, we can grab some of our data from that earlier problem. So it's 22.4 m plus 922.14 m equals 1/2 mv final squared plus 55 times 9.81, which is 539.55 m. It's 22.4 plus 922.14 minus 539.55 gives us 404.99 m equals 1/2 mv final squared. M's cancel. So divide by 1/2, take the square root. We get 28.46 meters per second. AC equals V squared over R. So in this case, the 0 G's, this is a little misleading. The 0 G's experience means that they experience a normal force of 0. So it feels like they are weighing 0. So to experience a normal force of 0, our Fg has to be equal to our Fc. So Fg would be mass times 9.81. Fc would be mass times centripetal acceleration. So in this case, our centripetal acceleration has to be 9.81 equals 28.46 squared over R. Cross multiply, 9.81 R equals 28.46 squared. R equals 28.46 squared divided by 9.81. And we get a radius of 82.56 meters. So to have that 0 G hill, we need a radius of 82.56 meters. So this combines Newton's laws, this combines circular motion, and this combines conservation.